Okay, so we just got a couple more reactions left. Hydroxylation. When you see this, when you see that mild ox reactant, this one's fairly easy. All you have to do again is break your double bond. So I'm going to break this double bond here. And always, if you see that mild ox, each of those carbons from the original double bond is going to end up with a hydroxyl group. So again, this is not an asymmetrical thing. You're only ever going to get one product. You just have to know to add hydroxyl groups to both sides. So break your double bond, add hydroxyl groups. So whether it was that original reactant, or maybe this one here, as long as you have that mild oxidizing agent as a catalyst, you just need to break your double bond, and each of those carbons that was part of that original double bond needs to have a hydroxyl group on it, and that's going to be your product. So this one's fairly simple. You just have to remember to do that when you see that catalyst. This one's a little bit more difficult because in oxidative cleavage, you're actually going to cut this whole molecule in half. And if you have a strong oxidizing agent, I'm not just going to break one of these bonds. I'm actually going to break both of those bonds and cut this thing in half, more or less. So remember that original molecule there has 4 carbons in it, 2 here, 2 over here, since I'm splitting it in half. But each of those original carbons that was part of that double bond is now going to have a double bond to an oxygen on them instead of being connected to each other. They're each connected to an oxygen. So you split it into 2 different pieces. So when this is going to be the hardest is when I start drawing something that looks kind of crazy, kind of funny. Sometimes it's hard to tell what to do with it. But really, make it easy for yourself. Just split that double bond. Remember, I need my catalyst here, so I'll draw that in quickly. You just need to split that double bond, cut it in half. I'll take one of those pieces, that top part, and I'm going to have a double bond to oxygen where that original double bond was. And then that other piece also has a double bond to oxygen, but they're separate from each other now. You got 2 different products there. One of the hardest examples of those that most people struggle with is if I have a ring to begin with, and I have that double bond between 2 of those carbons, and I have that strong oxidizing agent. You're supposed to break that double bond, but now this is no longer a ring, and you got to recognize what's going on here. And if I break that double bond, this is no longer a ring. So instead of going 1, 2 like I would have originally, I'm now 1, 2, 3, 4, 5, 6. So make a hydrocarbon chain with 6 carbons in it, and off of each end, off the 1 and off of the 6, there should be a double bond to oxygen. So if you can make that product, you should be good, but you got to recognize that you're breaking that ring. You still have to see how many carbons are there. You still need the same amount of carbons, but you technically don't get 2 different products in this example. You just get the one, right? It was still connected the other way around. You just disconnected that 1 and 6 carbon that were originally your 1 and 2. So these 2 products from before you had two different products because you broke that molecule in half. If you only break a ring in one place, it's still all connected some way, somehow. You're only going to get one product in that case. Okay, and finally, the last reaction that we have to go through is actually one of the simplest. If you're going to make a polymer out of ethene, right, two carbons with a double bond, you're going to do it something like this. I'll start out with just two of those ethenes. There's four of them total. But all you need to do is break this bond here and reform a new bond here, and now those two things are connected. You took two molecules and now it's one. If I take another ethene, I can do the same thing here, break this bond, make a new connection from here to here, and you can just keep adding to this growing chain as many ethenes as are available you can add. But what you should see here is that at the end, I had 4 ethenes that I put together, so I should have 8 carbons in this chain. So it's 1, 2, 3, 4, 5, 6, 7, 8. So although I could go through the process of drawing and breaking bonds and redrawing new bonds, what I really need to be able to do at the end of the day is if I have a certain amount of ethenes to begin with, say 5 of those, and I have my polymer catalyst, all I have to do is end up with 10 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the one thing you have to remember to do is there's always going to be a double bond on the end. I still had a double bond here because there was no new ethene to add to there, but you're always going to end up with one double bond on the end of your final product. So remember, 5 ethenes, there's 2 carbons in there, so there's 10 carbons on this side. So I have a decane drawn over here, 1, 2, 4, 6, 9, 10, with a double bond at the end between the 9 and the 10, and that's your product. So the biggest thing you're looking for is what number is here, because that's going to tell you how long your chain is, but otherwise just make sure there's a double bond at the end and you'll have your product, you'll have your polymer. Okay, so those are all of our reactions for alkenes and alkynes. We're going to have more later this chapter for aromatic hydrocarbons. Those things are different, so we'll get to that when we get to it. But this is good for right now. Hopefully it can help you get caught up.